Good morning, guys! So, ever heard of ionization energy?
Sure, that dude in Dragon Ball has about 9,000 of it.
Spot on! Wait, what? Nah, that's not right. We will find out what ionization energy actually means right now. Let's take a look at a sodium atom. If we represent the atom's shells, it looks something like this. As you can see, it has 3 shells and 1 outer electron, also called valence electron, in the outside shell. Ionization energy tells you how much energy is needed to steal this outer electron from sodium's shell. That means we need a certain minimum energy to get that sucker to detach. When it finally does, the sodium atom turns into a positively charged ion, a cation. Since sodium is now 1 electron short because we stole it, it has more protons than electrons. The sodium atom now has more positive particles than negative particles, and therefore becomes positive itself. It's like having just as many blue M&Ms as red ones in a bowl. Then, Dad comes along and just takes one of your blue M&Ms, probably without asking first. Now you have more red M&Ms in your bowl than blue ones. The energy it took for your dad to steal it is ionization energy. Since your buddy cares more about M&Ms than you do, it would take your dad a lot more energy to steal one from him. Stealing one from your brother, on the other hand, piece of cake. And elements are the same. Each one has its own ionization energy. That's why it takes different amounts of energy to steal electrons from different kinds of elements. Let's just take a look at this chart here. The elements of the first main group, like sodium, tend to require only a little ionization energy. That means it's less of a hassle to get their outer electron to detach. And then there are elements of the 8th main group, noble gases, that are playing hard to get and require much more energy. You can also say that the electron configuration of elements in the first main group is not very stable. In the 8th main group, however, it's really stable. The more stable the electron configuration is, the harder it is to take something from it. An electron configuration simply tells you the distribution of electrons in the shell. Well, for now, just remember, ionization energy tells you how much energy is needed to detach an electron from an atom. Also, it's different for every element. It doesn't really matter if that energy is thermal, radiant, or chemical energy. Also, it's usually measured in electron volts. What's nice about it, you can see right away how many volts it takes to get that electron. And even better, you get really nice numbers out of it. If you're more into joules, you can convert the electron volts into joules in no time. Now, you still have to pay attention to what kind of ionization energy we're dealing with. In the chart, we only look at the energy needed to detach that first electron. That's the energy needed to take only the least stable electron, the one that's easiest to take. Of course, other amounts of energy are needed to steal the second, third, whatever electron. Surely you've noticed that the energy within one period doesn't increase evenly. In the second period, it's beryllium and nitrogen who don't play nice with the others. Those little rascals lead us to the following conclusion. It's harder to detach electrons from full or even half-full orbitals. Since beryllium, for example, has a full s orbital, it's harder to get those frisky electrons out of there. The same applies to nitrogen with its fully occupied s and half-full p orbital. It's also nice to know that the ionization energy increases if you go from left to right within the periodic system. Makes sense, since we've already learned in our last video that the protons have a stronger pull on the electrons there. However, the energy decreases from top to bottom. That makes sense, since the atoms get bigger there and aren't as attached to the core. But now we should ask ourselves the most important question. Why do we need to learn this crap? This knowledge helps us understand what kind of bonds elements form and how they behave while doing so. Because electrons always play a role in forming bonds. For example, we can thus explain why noble gases are highly unreactive, or why halogens always require an electron from somewhere else without giving up an electron themselves, or what the charge on a sodium ion is, and above all, why Na bonds always form salts. In other words, why it gives up all its outermost electrons without forming a covalent bond. As you can see, the list of possibilities goes on and on. After understanding this, you will also understand everything about the electron affinity and electronegativity of elements in the next video much better. This way, you already have a better overview, so that you don't need to just continue aimlessly memorizing stuff. So what should you absolutely remember from all this? Ionization energy tells you how much energy is needed to detach an electron from an atom. Every element has its own ionization energies. Also, there are different ionization energies for different electrons. It's harder to detach an electron from a full or even half-full shell. We'll see each other again soon in our next video.